So this is Dr. P. Munaswamy, Professor, Department of EC. Today we are going to discuss about the Vsb Demodulation Techniques. So already in the last class we discussed about the Vsb vestigial sideband generation techniques. How we are going to generate the Vsb. It is a part of the one complete sideband and along with a partial part of the other sideband. That is Vsb. So vestige stands for a part of the other sideband. So that is the demodulation techniques. You can see so what is the Vsb? So Vsb modulation is the process where a part of the signal called as vestige is modulated along with the one complete sideband. The frequency spectrum of Vsb wave is shown here. So this is the spectrum of the Vsb modulation techniques. So you can see here. So one complete sideband. This is the one complete sideband, that is the Vsb upper sideband. Along with the one complete sideband, here we are going to transmit the another part of the other sideband. This is the part of the LSB, not a complete. It is a part, some portion of the other sideband called LSB. So one complete sideband Vsb. So this is the vestigial sideband modulation. We are going to transmit the one complete sideband along with a part of the other sideband. So because while coming to the receiver side, we can retrieve the original signal. So the generation or arrangement of the filter become very difficult in case of the transmission of the SSB. So there is a single sideband transmission. So there we are designing the filter to retrieving the original signal of M of t is become very difficult. So that to avoid what is the problem or drawback available in the SSB modulation techniques, that can be overcome by this vestigial sideband modulation techniques. So one complete sideband along with this a part of the other sideband. So is there any loss that can be maybe part of the other sideband? So there is a chance of getting the complete one sideband, so that you can easily retrieve the original signal without any disturbance, without any loss of the information. So then coming to the, so generation techniques of the DSB. So M of t signal, which is a modulating signal, and carrier signal AC cos of capacity, and M of t equal to AM into cos omega mt. So this after modulation, product modulator, so we are going to have the signal P of t equal to AC into cos of capacity into M of t. It is a product of modulating signal as well as the carrier signal. So it gives the two sidebands. The product of the two sidebands means which indicates the double sidebands. So it may be combination of the upper sideband as well as the lower sideband. So by the application of the Fourier transform, we can have the P of f equal to AC by M of f minus fc plus M of f plus fc. So here you can see the magnitude of AC by 2, and it is a M of f minus fc is lower sideband, M of f plus fc is the upper sideband. So it is a combination of both the lower sideband as well as the upper sideband. So then coming to the detection techniques. So because of the receiver part, so we are going to arrange the detection techniques of the Vsb at the receiver side. The receiver signal S of t is Vsb wave. So modulated wave of Vsb. So then there is arrangement of the product modulator. So because of we are suppressing the carrier signal, the one of the input signal is received modulated wave of Vsb, that is S of t signal, and for retrieving the original signal of M of t, locally you have to arrange the local oscillator which can generate the carrier signal AC cos 2 fct. So that way we are getting with the support of with the generation of the local oscillator, you can have the generation of the carrier signal C of t, which is equal to AC cos 2 fct. So that is the product modulator will get the input signals too. So one is the received signal of S of t, another is carrier signal which is generated by the local oscillator. So the output of the product modulator is gives the product of the both S of t and C of t will be indicated by V of t. So then, so there is the arrangement of the low pass filter. So why we are arranging the low pass filter means, so here because it is a demodulation techniques, detection techniques, our aim is how to retrieve the original signal of M of t. So the MFT signal, that is modulating signal, is always lies in the low frequency range. That is the audio frequency range, 20 Hz to 20 kHz. So that by retrieving the original signal of MFT, so finally you have to allow the only low frequency component, so that we are arranging low pass filter as a last component of retrieving the original signal in case of the detection of VSB. So that we are arranging the low pass filter here. So after passing the VFT signal, which is the output of the product modulator, to the low pass filter, so finally we are going to get the original signal V0 of t, which gives the original modulator signal M of t, originally initiated at the transmit side. So overall, there are three components: product modulator, local oscillator, and low pass filter. So by the product modulator, we can take the product of S of t and C of t. It is a low band pass filter. Output of the product modulator gives the V of t, which is a combination of the two side bands, upper side band as well as the lower side band. So our aim is, from this we are going to retrieve the original signals of low pass filters. That is modulating signal, low frequency components that can be allowed by the low pass filter. So then coming to the mathematical expressions. So here take the Vsb Scb S of t and carrier signal AC cos 2 pi Fct. So this is the standard input signal of modulated wave S of t, that is Vsb Sc wave, and carrier signal which is generated by the local oscillator AC cos 2 pi Fct. So from this we are going to have the V of t product modulator output is given by the carrier signal input and the received standard wave S of t. So it is a product of the AC cos omega Ct into S of t. So after application of the Fourier transform to this one, we can have this expressions: V of f equal to AC by 2 S of f minus Fc plus S of f plus Fc. So you know that from this, the mathematical equation for the Fourier transform of the original signal M of t is given by S of t equal to AC by 2 M of f minus Fc plus M of Fc plus Fc into H of f. So it is the filter transfer function H of f. So low pass filter. So with the support of the low pass filter only, we can eliminate the high frequency components and allows the only low frequency components. So that is, we are converting the what is the output of these S of f minus Fc plus S of f plus C. So these are the lower side bands and upper side band. S of f minus Fc lower side band. S of f plus Fc is upper side band. So combination of this one, by replacing the other things, we will get these equations. So finally, we are going to get the what is the S of f plus equal to AC by 2 M of f plus 2 Fc into H of f plus Fc. So from this we are going to generate the substituting these values. So what is the final output of V of f equal to? So AC square by 4 M of f H of f minus Fc plus H of f plus Fc plus AC square by 4 M of f minus 2 Fc into H of f minus Fc plus M of f plus f2 Fc into H of f plus Fc. So from this you can say that it is a combination of the both the upper side band as well as the lower side band. So by this substitutions, we are converting into the frequency domain, which is available initially at the time domain. So in this above equations, the first term represents the scale version of the desired message signal frequency spectrum. It can be extracted by passing the above signal through a low pass filter. So previously, it is a combination of the both, so upper sideband as well as the lower sideband combinations. So from this equation, you can say that so the low frequency components can be allowed. So that is the arrangement of the purpose of the low pass filter in diagram. So here you can see the low pass filter after the product modulator, which can allow the only low frequency signals. High frequency components can be eliminated or rejected. So that finally we are going to have the what is the output V0 of t, which is originally a low frequency signal. So that is, here we are going to have the V0 of f equal to AC square by 4 M of f into H of f minus Fc plus H of f plus Fc. So this is the filter function spectrum and modulating signal AC square by 4 M of the modulating signal frequency. So here we can say that from this above equations, the first term represents the scale version of the desired message signal frequency spectrum. It can be extracted by passing the above signal through the low pass filter. So that is the, so what is the function of the, what is the use of the arrangement of the low pass filter? You can easily say that. So because of this modulating signal is always lying at low frequency range, that is audio frequency range. Generally we are generating the sound signal. That sound signal can be converted into electrical signal, and then there is a modulation and transmission. Coming to the receiver side again, the modulated signal, high frequency signal can be converted into low frequency by the operation called demodulation. So after that, we are going to have this entire process. So there is arrangement of the received Afdsb signal and another local oscillator which can generate the carrier signal frequency. So by the both inputs, the product quantity which can generate the product of the both input signals. From this, we are going to have these two signals can be represented. So among these two signals, which are high frequency components, can be eliminated, and low frequency components only allowed. So that is the final purpose of the low pass filter, which can allow the only low frequency components. So that is given by V naught of f equal to a square by 4 m of f h of f minus fc plus h of f plus fc. So this is how we are going to get the original signal of the demodulation Vsb. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.